Okay. So welcome to our first class. First class this summer. This is Dynamics Machinery, ME 6710. I'm Steve Canfield, your instructor, and for reference, the class is here if you're online. And now that we've seen that, I'm going to just stop the video because I'm going to flip this tablet around. Flip this thing around and become a tablet. Easier for me to write. Okay, I've got an agenda plan for today. We're here for 2 hours today. First, I want to do intro things. We've got a bunch of intro things to do. Talk about the website, MATLAB, our programming platform, schedule, syllabus, and the like. I'm going to try to stay on track. Plan about 15 minutes there. Then I have Dynamics and Machinery. This is what I would call a classical rigid body dynamics class. Some schools call it intermediate dynamics. We kind of get up to the verge of chaos but stop. We call it dynamics and machinery, so there'll be the focus on machines. So we'll be looking at multi-body. I look at machines as being multi-body systems. So I'm going to give an intro, kind of just a big picture overview on that of dynamics in general. So that'll be I've got 30 minutes scheduled there. Then I want to spend the rest of the day as a little bit of a background, get us up to speed on dynamics problems. So I've pulled out 3 or 4 sample problems. So we're going to just march through. Now this is an academic class. These are academic problems, but we will work to try to connect. We're going to go back and revisit our academics. You guys are all practicing, mechanical, electrical, dynamicists, analysis people. These problems are going to be more academic, but we're going to go back and review those skills and then work as we go along to apply them. That's the third thing. So I've got 3 problems scheduled. Then finally, I hope to get through that in about 45 minutes. That'll give us about 30 minutes left. The last thing I wanted to do, well, I guess at the very end, I need about 5 minutes for homework assignments. Does that give homework in the summer? Oh. At this point, once you hit 25, right, there's no such thing as summer that goes away.
That's right, yeah.
Yeah, so homework. My goal is to give you a homework every week, so we'll look at the homework. And then I want to do a little review of some machine examples. And I've pulled some examples, so I've got about 30 minutes there. So we'll do about 25 minutes of machine examples and then, homework and prep for the next class. So that's the agenda. I'm going to try to watch my time because I want to cover each of these things to make sure we don't get over. And then I have examples printed out on paper that I'll show you. Okay, good. At any point, just jump in and interrupt me, stop me, add discussion along the way. Okay, so let's first look at the intro. On the website, here. On the first thing I want to show you is the website I'm using. We have oops. Help Windows 10 people. How do I get to my other stuff I had?
Switch back to exit tablet mode.
Oh, yeah, okay. That's a good idea. There we go. There, okay, thank you. See, Tommy, don't go far. You guys see. Okay, this website, okay, at the moment I'm putting stuff here because I didn't know if you were in iLearn yet. And it's just an open site. So this is just my tech website. But if I sent the link, but you just go, it's sites.tntech.edu, scanfield. If you click on the education tab, I need to get our class, click there. But if you just click on education, and again, I will make sure that you guys have that, and then scroll down, you'll go to our class website. Okay, so this is the first thing that I want to make sure we see. And I'm trying to organize this around the section that we have. So the first thing that we have are class details. I've posted the syllabus here. I did not bring copies of it, so we'll jump in and look at it here, okay? If you want copies, let me know. I did not bring hard copies of that, but the syllabus is there. Programming assignment for MATLAB. or excuse me, programming assignments. I have 2 programming assignments called out, but along the way we'll be doing those. And I'm proposing we work on MATLAB, and all of you have access to MATLAB for free. And I've got the link here that walks you through that. So, you know, if you're willing, go ahead and get that MATLAB. Tommy is an expert at getting it. And then mail me.
Way or not. I may have done it the tech way.
Well, this is, I just grabbed the sheet from tech. Yeah, it's the same. It should be the exact same one. This is now the, this is, you know, we renewed it. So I think this gets you the current version. It should be pretty straightforward, but if you have questions, contact me or Tommy. Yes.
Are we going to have that on a computer in class, or is that okay just to have it
for homework, and you know what? Actually, I don't have it on this computer, but I will try to spend some time in class where I'm showing you examples. So if you happen to have it on your laptop, you could follow along, but not necessary. Not necessary. Okay, so that's where you go to get MATLAB. And then, you know, I need to make sure we stay organized, but I've tried to list, today we're going to do an informal dynamics review, and I posted the examples that we're going to work. They're actually worked out there. We're going to work them out together. They're posted there. The next topic is particle kinematics. And, you know, particle kinematics, we're, again, doing a review. At the top, I've listed my handwritten notes for those if you want to see the physical notes. And I indicated that some of this stuff would be offline that we would look at. So here are a series of lectures. These should last between 5 to 10 minutes each, and they're very topic related. So an overview, looking at Cartesian coordinate, you know, just a review of Cartesian coordinate systems, path-dependent coordinate systems, cylindrical coordinate systems. Some of them come along with an example. So one of the things I'm not going to lecture on this one. So I want you guys to go through those, okay? So watch those. I just had Ben that logged in. He just checked those for me last week, and he said it took him about an hour or 2 to go through those, okay? And again, I've got the entire set, my handwritten notes that these build on are tucked at the top. So watch those. Reviewed those. These topics are not covered as thoroughly in your text. Your text kind of breezes over that stuff, you know, and yeah, there's 4, 5, 6 texts. You know, once you get to this applied dynamics or intermediate or advanced, whatever you want to call it, at the graduate level, books come in. It's a little hard to get books. They come and go. The classic ones are all out of print, and I was a little worried about doing that. So this one's still in print. That's why I selected it. This topic's not strongly covered in the text, so I wanted to make sure we had that. Okay. Next week, when we look at the syllabus, next week we will be covering rigid body dynamics, and I'll jump into that lecturing together on that. But I do have also the lectures for that recorded, again, in this little module. So, you know, there's about 10 or 15 of these, and they should be about 10 minutes each with a bunch of examples below. This rigid body kinematics is really where we jump into the workhorse of building dynamic models, describing motion in 3 dimensions. Translations are easy, the same as 2-dimensional. Or, you know, orientation is the problem, right? And we can't treat orientation as a vector. So we need to practice, you know, one of the methods that we'll use to describe orientation. And then we get into dynamic methods. And this is sort of an overview of where the class is going. I do have a section where we evaluate differential equations of motion, although we haven't quite derived them yet, so I should probably move that down. In this class, we'll look at Newtonian methods, vector methods, and then analytical, and that's where my current preparation stops. Then we'll go into analytical methods. So you'll see both. This will be a vector mechanics approach and analytical mechanics approach. We'll have both. They both yield the same results, but they are very different ways of looking at the problems, and they each have their pros and cons. And then we have a series of applications. Okay. So that's the website. That's what I have on here. I'm asking for next week that you watch these, you know, so that would be, you know, I really have 2 assignments for you for next week. Actually, let's make it 3. 1, go ahead and download MATLAB. I guess we'll just do it right now. Let's make our assignment now. We'll get those 5 minutes at the end. 1, download MATLAB. And if you have a problem, communicate with myself, Tommy, someone else that has some problems. If you communicate with me, I'll probably connect you with Marvin, our technical person there. Number 2, watch the lectures under particle kinematics. I'm estimating that that's about an hour and a half of lecture time. Go through it at a high level, and then we'll have it for discussion. And then we can do a discussion when we get back together. And then the third is your homework. And the homework I've pasted at the bottom, and so far I have 1 homework. My goal will be to have 1 homework a week, but we need to kind of feel me out how these homeworks, are they enough? Are they too much? Maybe what I need to do is have sort of practice and homework problems, so that would, if I can get a little more organized, practice problems and then homework problems. These I've got to have cleaned up. These I want to practice and get results. Okay. But at the moment we'll stop there. I think there's like five or so problems on this. All right, Tommy, going back to tablet mode. So thank you, help me out there. Okay, so there we and the syllabus. Let's look at the syllabus. I jumped too quickly. One other thing, if someone can remind me, I would like to remember to stop the recording at the 1 hour mark and then restart it. So I think I should have 2 recordings so that things don't get too large. I'll try to remember to do that. Okay, so here's the navigation page. Okay, so here's the syllabus you can all look at. I have my contact information. If I haven't shared it in particular myself, please call me. Yeah, my cell's the way to get a hold of me, okay? Just call me. Feel free to reach out to me anytime.
Those times are central, right?
You know what? Those times are central. Actually, yeah. Yes, those times are central. This is going to be hard for me. I got here on time today. Oh my goodness. You wouldn't think that something like that would be as hard.
It really is, and it won't change.
I know, it's something so simple. I learned that like
on one side and I had to go.
Yeah. Okay. Prerequisites, approval instructor, we're all good to go there. The text is the applied dynamics that you have. Applied dynamics. This one's the one. Okay, all right. So looks like we all have it. It's an okay book. And it was available and not terribly well priced. I didn't show some references. There are a number of references, and I have these, and if anyone is wanting to, you might have them in your library, or if you want, you can borrow one of mine. Some of the classical books are the Greenwood. It's really thick. It's probably 3 or 4, courses thick, frankly. But there's the Greenwood text. Again, this one's out of print. You can get it on Amazon. I was just nervous of choosing a book that was out of print for a text. And then the Myrovich book is pretty classic, and it's way out of print. But this one by Haim Baru, which is the one I had been using, but it's been out of print now at this point for quite a while, so I was reluctant. This one sort of is a Myrovich-like, It's really deep. These books are sort of the books that make a lot of sense after you take the class. And this book tends to be a good one to kind of get you through it. So these are a couple references that I just wanted to bring and comment on. Okay, we have the course description, objectives. Feel free to look at those. Major teaching methods, we talked about those. Topics. Great. Okay, grading. Let's take a look at that. So I have in mind 2 exams, and I've got a schedule below. So one kind of midterm and one final. Homework at 25%, and then programming assignments. I guess I took a few points out of the final or the exam 2 and moved them to programming.
Is that in class or take home?
The exams? You know what? That is we probably wanted. Hadn't crossed my mind until you just mentioned it. Probably just to be flexible with our time, we might just do a take home. I have accounted a class period for them. let's see how that goes. The one thing I find faculty do when they say take home, they take a normal exam and explode it into like 6 exams.
Yeah.
So I'm always reluctant, to say take home.
Do that.
Yeah, exactly. It's like, I would rather just sit and take a normal test. So I mean, my goal when I do a take home is to give you the same class exam that you'd have in the class is my goal.
What's our average on our last take-home test? Mine was about 24 hours.
Okay.
Yeah, they were long.
I don't know what. Yeah, it's like, oh, take home, that shouldn't be a problem. And it's like, I would have much rather just studied and taken the test. Yeah. Okay. Well. Yeah. Well. Okay.
6 hours for the first problem.
Anybody get their final back? No.
Yeah, the graduate courses are sort of the Wild West of academics. Okay, grading, normal scale. Student academic misconduct, the Wild West? Okay, shoot from the hip here.
Well, we gotta have a B to get paid.
Oh, yeah. Now you're thinking, Lynch, hang him high. Maybe, I'm going to turn the class around and stand next to the door next time. Okay, attendance policy. This is my normal thing that I put in everything. Actually, we're required to put all this stuff in, disability accommodations and the like. This is this is not a usual class. Okay, this is a special class to me. So frankly, just let me know, keep me directed, communicate with me on anything that I can do there. Okay, really what I want to show you then is I had a course schedule and I'm 3 minutes past my first time, so I got to wrap this up. So I threw out a course schedule for each of our classes, and I need to bring up one thing here, okay? When we met, I said, hey, I got this idea. We'll meet once a week and we'll do stuff online once a week. I got cold feet, okay? I want to make sure you're getting plenty of all of me, okay? I want to make sure I want to make sure we're getting our time together. So I would like to propose this. I'm going to, I've committed to recording and doing these things online. So I want to propose that on Tuesday mornings, the same time block, I will be at Tennessee Tech, and I will probably focus a little more on practice problems like we alluded, but I will be at Tennessee Tech. I've got a nice room set up, and kind of go through stuff here. I will record it so you can watch it after the fact. And if we can find a room here where we can be and you can, hopefully try to have some back and forth a little bit. Okay, that's my proposal. I'm putting that on the table. We can have a few minutes to discuss. I know you guys have busy work schedules, and this is kind of a last minute thing. I say last minute, but I'm wanting to make sure we have a little more time together. So I'm going to propose that. I think that would work around your travel schedules and the like. Give you the option if you want to be, if you can be collected in one spot, great, you can join, or you can sit at your desk and watch, or you can record afterward. And I'll make sure we get those extra times in because, time flies by here. Okay, so I'm proposing that. If there's discussion now, let's have it. If you have some other issues, catch me after class, and then, if I need to adjust it, I will within the 24 hours. Otherwise, I'm proposing that. So based on that, I've got a 2-day schedule from here on out. So here's June 8th. And then based on that, we've got a kind of a 2-day schedule from here on out. This week will be our introduction, some basic kinematics, practice problems, kind of a review. Next week will be rigid body kinematics. The third week will be Newton-Euler equations of motion. So we'll jump into full, all those rotational.
The 13th and the 15th.
I might have those. Oh yeah, 2 days apart. Okay, the rest of them I think look right. That's a good call. It is intended to be a Tuesday, Thursday on every class, and so on. Okay, so this is my proposed schedule. Over on the right, I've tried to call out the things, the online lectures that you can watch, but also by doing this, other than the particle kinematics, I'll at least touch on everything. Okay. We'll touch on everything together. And then I'm proposing, I guess at the moment I've put exam 1, I could have put it, okay, this July 4th, there'll be no class, that July 4th. I'm actually on travel that week, so we'll kind of look at that and see if we want to just do a fully recorded that week or what. Although I'm planning on recording everything. So no class July 4th, I didn't put that in obviously. And then I guess right now I'm targeting that exam, but frankly, if we do a take home, it'll be kind of in this window of time. So that's right at our midterm, and then moving down. We'll do the Newton-Euler vector dynamics above, then we'll get into analytical methods below, and then I've got two, depending on as time permits, 2 to 3 applications that I want to do. One is a multi-body and some flexible system. So I'm working this summer actually on another E-sail. It's an E-sail. I'm working with NASA on an E-sail problem. It's another tether dynamic problem. And so I thought that would be a nice one that we could review together. And I'm doing some experiments on the flat floor. So maybe I'll even have a little data that we could build a model and compare it to some data. And then the other one that I was going to pull, my other area of interest is robotics, particularly mobile manufacturing robotic systems. So I thought that we'd have a second application in mobile systems, and that introduces these things called non-home limit constraints. So I want to talk about that. And then the last week, there's just one class, so we'll have our exam and then wrap up. Okay, questions on the schedule, comments?
The program column, you have the program assignments. Are those the due dates? Those?
Very good question. Very good question. I put this together kind of yesterday on the fly. So that's the tentative, tentatively I'd like to have one that's kind of, I think I had that right after that week. And so tentatively, yes. Yeah. It's not, I guess what I'm saying is I don't have a firm day on there. Okay. But yes. I want to be careful that I don't let us push everything toward the end. Okay, other questions, discussion. Okay.
If we end up being 2 classes a week, are we still going to meet for 2 hours?
Yeah, let's meet the 2 hours on Tuesday and 2 hours on Thursday.
The classes you're going to broadcast, are those going to be on that Zoom website?
Yes. Yes. And so what I'm going to do, now that's agreeable, I'll go ahead and just schedule the summer and send that, or I guess I could schedule each class or schedule the summer. I'm not quite sure how that works, but the answer is yes. So what you got there, you don't need an account or anything. You just go to the website and you need that 6-digit or 9-digit number, and just type that in, and you'll, and we're going to
That's why I asked.
The KC2 conference. Is that different from the website?
It's kind of like GoToMeeting.
it's GoToMeeting.
Is it GoToMeeting?
Well, no, I'm sorry. It's just like GoToMeeting, I guess yeah.
So that's only if you want to watch it live.
Yeah. So right now I am recording this.
Right.
So I don't think I have any, I don't know if Drew's logged in. Drew said he was on travel. He told me he's on travel, so that's why I wanted to make sure I at least tried it. Yeah. Okay. Let's move forward. Now it's time for our overview. So, okay. And don't mind, I'm going to sit here, maybe try to help my. Okay, so it seems that it's nice to have a little bit of overview time, a little time to get up to speed. So now I want to do an overview of dynamics, kind of big picture. To some degree, dynamics describes the whole world. So we need to zoom in quite a bit. So let me just give a few characterizing things. We're going to be looking at 3D, 3-dimension, the kind of the complete spatial dimension as we understand it. I will do a fair, 2D is a subset of that, and we will do a fair number of 2D problems, but the methods we'll develop will be full 3-dimension. We're going to be looking at multi-body systems. And the concept with multi-body systems is you have these internal constraints. That's the problem. So, the classic undergraduate dynamics you typically look at single bodies which avoid those constraints, and then how do you deal with them? So we'll include that. And then primarily we're going to be looking at rigid body systems, which means, dynamics is based on the concepts of calculus. By making our systems rigid body, it means that we can look at differences or differentials in time only. We don't have to worry about differentials in space. With that said, if you notice, one of the applications I proposed was a flexible tether, and introduced that particularly so that we could see how we could start introducing some non-rigid body characteristics into the models. Okay, and then okay, and then the other thing I should say is the words linear and nonlinear. We always throw this system's linear, this system's nonlinear. It even confuses me sometimes. Is it linear? Is it nonlinear? It goes back and forth. You know, as a rule, we live in obviously a nonlinear world. As a rule, nonlinear systems are just almost impossible to handle. So as engineers, we try to make things as linear as possible, okay? Going back, as a rule, dynamic problems are nonlinear. It's not the dynamics generally that's nonlinear, it's the kinematics, but typically that's the case. We will spend a little time looking at linearizing systems, trying to decide what systems are well suited for as linear systems and what are not. When it comes to addressing them, the linear systems, we can get these closed form solutions. We can look at the characteristics very nicely, almost analytically, by writing sort of closed form solutions. Nonlinear systems, we just treat with software. We typically numerically integrate. And, that's the workhorse for you guys. I mean, you run everything there. So frankly, nonlinear systems, to me, it's a little bit academic a lot of times when you constrain yourself to linear systems, although we do it. If you got to design control systems, you try to work with, you often linearize. Okay, so that's just an overview there. Okay, so when we look at dynamics, I want to now look at the methods of dynamics. And the first method, the classical method I'm going to start are Newton's laws. Okay, and so now this is overview / review land. Okay, and at any point, I've got notes, comments along the way. This is a quick review. So use this time to bring up questions, comments, discussion. So Newton's laws are our primary thing. And I am not going to go back and do the quizzing on the, all the little nuances that you had the first time around. So this is meant to be more of a discussion right now. So, Newton had 3 laws that he proposed. Sometimes you look at them different ways of getting at the same animal. He had his N1 through N3. N1 looks like a conservation of momentum. Which is that, he says if F equals 0, then A equals 0. His N2 which is sort of our workhorse, that force is proportional to, and, we write it as MA. But sometimes, you can also think of it, and these are vectors, I'm just writing this down quickly. You can also think of it as the time derivative of a momentum. And of course, these are vector laws. And then N3 is our action reaction. It's what we use in, for constraints. N3 is constraints. Later on, we always ask ourselves these things. Is this what was going through Newton's mind? Maybe, maybe not. It's hard to know. I mean, obviously, one of the most brilliant people in that class. But we can ask, at least after the fact, we can ask ourselves, well, why did Newton why 3 laws? Newton, why 3 laws? Again, I'm not sure that this is the answer he would give, but why 3 laws? But let's look at them briefly. So N2 is how we solve dynamics. N2 leads to our equations of motion. That's what we call these things, equations of motion. And I'll just start writing them EOM, cap, or lowercase. These are the equilibrium. This is the equilibrium, the fundamental equilibrium principle that governs all of physics. So that's why N2. But why the other 3? Well, I mentioned already, N3 a lot of times gives us constraints, or to some degree defines kinematics, which is a definition of the constraint. So it's maybe what I'll call kinematics, or statics if it's not moving, but kinematics if things are moving, constraints. And then why N1? What about N1? Well, N1 defines, and this is actually an important concept I want to mention. N1 defines a reference system. And in particular, it defines what I'm going to call an inertial reference frame. Maybe we could call it an IRF, an inertial reference frame. Sometimes, we could call this a Newtonian frame. These are different names we could give it. An inertial frame. Typically, we call it an inertial frame. Sometimes you might call it a ground frame. Okay? And so what's the concept here? What's the concept? Well, the concept is this. Do Newton's laws apply everywhere? Those, back maybe when you were in college, maybe if you were kind of a nerd, which face it, guys, you all were, right? That's why you work here. And, you know, and you'd be at, you know, the cafeteria and you say, you know, there's this kid on a spaceship, you know, and he's tossing a ball around, and a train goes by and they watch him, blah, 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 right? And you stump yourself. It's like, it doesn't work. You know what? Newton's laws don't work, okay? Or do they work? Or it doesn't make sense, you know? So you work at it. So here's the question. Do Newton's laws apply universally? Well, the answer could be yes or no. Yes, if you apply them in an inertial reference frame, okay? That's the requirement. You must apply Newton's laws in an inertial reference frame. Newton's laws don't apply in a non-Newtonian or a non-inertial reference frame. And Newton defines the frame with law 1. That frame is defined as a frame in which no force implies no acceleration. And we flip that around. We say a Newtonian reference frame is one that's not accelerating. And in such a case, a mass, a body that's not accelerating, will require no force to maintain equilibrium, okay? So that's the concept. So a Newtonian frame, an inertial reference frame, is one that's not and that's a bad one, that is not accelerating, okay? So that's the main idea. So Newton's laws work in that frame, and they don't work in a frame, you know, it's not a Newtonian frame. Okay, quick question. I'm not accelerating, am I? Is this, yeah, I mean, here, let's attach a reference frame to the corner of this room. Is that a Newtonian frame? No, it's on the surface of the Earth, right? And the Earth is rotating. You know, that creates accelerations. Okay, so I'm going to put my frame at the center of the Earth. You know, fix it to the exact center of the Earth, so it's not or excuse me, I'll put it at the center, but not rotating. I'll let it not rotate. Was that fixed? No, because the Earth's going around the sun. You know, it's great. I'll put it in the sun. Well, the sun's moving. You know, is there such a thing? Does it exist? You know, my understanding, I watched that little thing at the STEM Center. Apparently, the universe is kind of doing these waves. So it is a theoretical construct. To our understanding, we don't know that there's any point in space that's not accelerating, okay? So from that standpoint, you know, you could say, well, Newton's laws just don't work, okay? However, but it gets back to engineering, all right? So here's the thing. For the problem that I'm doing, the acceleration, you know, my frame is attached somewhere. So if we're working, you know, if we're working on a machine in a factory, or, you know, some robot that's taking samples, my reference frame that's fixed to the ground of the floor, does that work? Well, the accelerations that I'm ignoring, are they significant to the problem? If they're not significant to the problem, then that is a fine frame, okay? Working with machine tools on Earth, you know, depending on the precision, you know, for almost all cases, those work just fine. If I'm sending a satellite up, you know, to low Earth orbit, you know, my frame fixed on the Earth is not good enough, right? I need because I'm worried about a lot of things that take place. So that's the concept. Does that make sense? Okay. A little academic there, but that answers those problems of, you know, the boy on the spaceship moving around, okay? Moving around, okay. And then we just mentioned N3 is our action-reaction. Okay. You know, Newton created those laws. It's kind of interesting. You know, Newton wasn't the first to mention those things. I remember, you know, Galileo basically, you know, a lot of people had that idea. He framed them very well. It's classic. We grant that to him, though, and that's fine. You know, his law of gravity is probably his more unique contribution. Well, here I'm saying, oh gosh, Wild West. Newton's going to show up and club me over the head, okay? But people tend to say, not me, but that his law of gravity is kind of his big, unique achievement. And his law of gravity is that F is proportional to the two masses, M1 and M2. So the force between two masses, what I should be saying, is a product of the two masses divided by the distance squared between them, and then he threw in this gravitational constant, G. If you look in the back of your dynamics book, they'll use the term mu, and I think mu may have the mass of Earth tacked in. So you can actually calculate the gravitational constant for a body anywhere, here, 100 miles, 50 miles above, at sea level, above or below, you can do that. And it has, Earth's magnetic field. Now, there are a lot of perturbations to that, but that law works well if you assume the Earth is a sphere. Okay. Okay, there are a few problems, and I'm gonna get beyond. So, Newton's laws, are they good or bad? Well, the world we see is built on them, so I guess we can't complain about that. They're not really built on, I have here written my notes, they're not built on experiments, but there was what was the space probe, the Newtonian space probe that identified gravitational waves and started to provide some early experiments to help validate a few years back. So your textbooks might say that Newton's laws are not validated with experiment, but there was that, I guess it's 3-4 years back. I should pull the name of that spacecraft. It was checking gravitational waves, at different, at these spread out locations, and could actually see them, and measuring Einstein stuff as well. So these things are coming along. Okay, what are the problems though? Well, the inertial reference frame is not a problem. You just have to be aware of that. But they don't work. They don't work in a relativistic sense. Okay, so the two. Well, really, the main problem are you got to be lower speeds. So it does not work. Does not work at high speeds, and here by high speeds, I'm talking, the speed of electromagnetic waves or speed of light, or even approaching it, c. And what is that? That's like a 3e⁸ meters per second. There are corrections. For what it's worth, there are corrections that you can apply to Newton's laws to help make them more accurate if you're doing there. They don't apply. They don't work in quantum mechanics. They do have some problems with very large masses, but I'm not prepared to say how large those masses are, so I'm going to skip that off. Kind of related to the light, Einstein and Newton give different predictions on starlight bending, and Newton is wrong on those. So again, you can, people have built correctors for that. So I guess what I'm getting at is, Newton works great for terrestrial systems, space systems, but you got to know the bounds, speed, mass, the reference frame. Those are kind of the limits around that. Those limits are, really outside the scope. Well, I say outside the scope of this class. That's not the case at all. I mean, the spacecraft dynamics that are used to track and monitor things are based solely on the principles that we're talking about here. Okay. So, that's my first overview. Now, Newton, as Newton writes it, F equals ma, that's fine, but we got this concept of rotation, right? A is translations. So how do we extend? So the second thing is to extend Newton to rotating systems, or orientation. And a lot of times we attribute that to Euler, and it leads us to these Newton-Euler equations of motion. And the Newton-Euler equations are coupled. They're the F equals ma, which works for the translations, and there's the sum of moments equals I alpha. Okay, everything looks nice and pretty, right? M for I, A for alpha, F for M. And M is the sum of moments, and this really should be the sum of forces. And we are going to break these down. I mean, we're going to break this stuff down. This is the overview, right? But does the story stop here? No. There are other terms, and the primary term, we call it the gyroscopic term. So with rotating systems, there's more to the story. And it is the fact that, the mass doesn't change when it moves. I mean, as long as you're not purposefully changing it, right? Mass doesn't change. But the mass moment of inertia changes as it rotates. And we have to account for that. I mean, just from your perspective, right? It's pretty simple, right? This book looks different to you, right? You can imagine the mass, it looks different as it changes. We have to account for that. So that shows up in this gyroscopic term, okay?
Is that omega cross I omega?
Yes, that is omega, yes. I'm being sloppy here. So omega is a vector. So omega is an element of R3. It's a vector, a three-dimensional vector. Omega X, omega Y, omega Z. I is a 3x3 array, an inertia tensor, a 3x3. So this would give you a 3x3 times a 3x1 which gives you a 3 by 1. So this together is a vector crossed with another vector, which gives you a vector. So that's how it breaks down. This is actually the momentum. You could write, it's a meg across the momentum. And that is the gyroscopic effect. And all kinds of things explained by that. Okay. So, this applies now to rigid bodies. As Newton applies, it's to particles, although a purist would say, well, I can just, create my rigid body as a series of particles. That's actually how you get Euler's equations. We will derive that together here in a little bit. And it's a classic method. Newton and Newton-Euler are these vector, the key idea, I say the key idea, and idea is these are vector methods. Okay, these are vector methods. Preston, as you just said, these are vectors, right? In a way, the force is the force. It's a vector. You might, if we sat here and said, well, duh, what else could there be, right? What else could there be? Well, what if instead of forces, I want to talk about energy? Rather than characterizing my body based on the forces acting on it, what if I want to characterize it based on the energy? Energy is not a vector. What if I want to characterize it, I don't know, based on something else, some power density function or some Fourier transform? I'm just making stuff up, okay? I can't do it. I have to have vectors defined specifically this way. So Newton sort of ties your hands to these vector-based approach. Free body diagrams, draw the vectors and solve. It works remarkably well, but I'm just kind of telling you the range of it. Okay, questions on that? Now, that's not where the story ends. So Newton was wildly successful, but there are other ways of looking at these fundamental principles of describing how the world works. Okay, so I've listed Newton and the Newton-Euler as sort of 1, 2. So I guess if we move on, then our third thing will be an alternative way, and I'll start with the method I'm going to call virtual work. I said I'm going to call it virtual work. Yeah. Everyone calls it virtual work. Virtual work is attributed to Johann Bernoulli. What did Bernoulli not do? There's a few people. It's like, what on earth do these people not do? There are like 20 Bernoullis. Actually, there were quite a couple Bernoullis, but this Johann Bernoulli did so much. Okay, so the concept of and I had dates somewhere, but all these things happened at the same time. These were circa the 1740s, maybe. I had some dates here, just for fun. I need to move on. Okay, so the concept of virtual work is this. So it's a work method. So the concept of virtual work is that the sum of all the forces, so I'm going to sum over I, so I are the forces acting on the body, and these are the forces, I'm going to call them A, for these are the active forces, or the forces acting on the body. And to help describe what do I mean not constraint forces. These are not constraint forces, okay? The sum of the forces dotted with the virtual displacement of the body equals 0. Well, that's the statement of that's the statement that we now call virtual work. Remember, work, or a little infinitesimal work, is a little f dr, right? So the work is the integral of f dr. So you can see this is just f dotted with r. Now it's not a dr, it's a virtual r, and we'll come back and review that. But effectively, at the moment, it's the same thing. And the work on to be in equilibrium, the work on a system has to be the work has to be 0. That's the basic idea. We morph that a little bit, divide by time, and then practically we'll end up saying, and I'd like to do an example today, which is that the force dotted with the velocity. So if we just divide that virtual work statement through by time, we can get the force dotted with the velocity equals 0. So this is a virtual work statement. And the big idea here is that this gets rid of, the whole idea here is this gets rid of, sorry. Tell me if I've moved too far. This gets rid of constraints. Okay. That's the whole idea. And it's a work method. Work is energy. So this is an energy method. Virtual work is the gateway to the energy, an alternative way of looking at problems, okay? And it gets rid of constraints. You know, when you write Newton's equations, you know, you've got all the forces acting on the body, constraints, external forces, whatever you want to call them. Virtual work looks at just the active forces. The concept is constraints don't do work, you know. Preston, I'm more practicing names. I peeked here. Keep on up. Jason's sitting on that chair. You know, there's all kinds of forces acting on Jason, but is Jason, you know, not mental work, but is Jason doing physical work? No, he's not doing physical work. Well, you say, well, wait, what about all these forces acting on him? Well, they're canceled, right? So you know, you're sitting there, the force, you know, there's a force of the chair acting on you, but it's equal and opposite to the you acting on the chair. You say, well, fine, but I'm not moving. What happens if I move? Well, if I move, you know, the force, that constraint force is now moving, is creating work, but the work of you on the chair is creating equal and opposite work, so it cancels. So that's, you know, fundamentally the idea. So all the constraint forces are gone, and that's the idea. Now, the issue, virtual work sounds great. The issue is, you know, it's static. You know, I don't have, you know, this is statics, or it's a statement of static equilibrium, you know, in its original form, in that form. Okay. So what do we have next? So that was number 3. So the next extension that I have here is, sorry, I didn't have Johann Bernoulli. The next thing, and this is a story that I'm creating for you a little bit, but it's a timeline that we look at, is D'Alembert's principle. And this is attributed to Jean-Laurent D'Alembert. I guess he's French, sounds French. And this one I actually have the date, 1742, but all this stuff kind of came through around this time. And D'Alembert, with D'Alembert's principle, we can take virtual work and extend it from statics to dynamics. He effectively said that we can take, you know, if we look at this F equals ma, Newton's law, we can look at this as a, you know, there we look at it, it's mass times acceleration. It's the quantification of the inertial force on the body. Well, he said, well, let's just call it a force. So he creates that inertial force. He calls that some FO. So let FO equal this MA, or actually let FO equal negative MA. And if I do that, I can then say the sum of all my forces, let me call them all my F tilde with F tilde equal to my F plus my FO, you know, equals 0. So now it makes, you know, D'Alembert kind of made dynamics look like statics, right? Sum of forces equals 0. That looks like a statics problem, but the inertial effects are now accounted for as a dynamic force. Seems kind of trivial, but these are building blocks, okay? And then, oops. Yeah, I'm going to ignore that at the moment. My recording should be local for what it's worth, I hope. All right, so when you combine, maybe I can call this 4.5. So if we combine virtual work and D'Alembert, we now get, you know, a method of virtual work that could apply to dynamics. We can now apply this energy method for dynamics. And one of the ways that do that are a method of virtual power. So virtual power. Which is sort of one such way. And over here on the left, I'm going to put I need to put a little symbol. We're not going to spend a lot of time with virtual power. It's a, you know, it's a great method, but I'm not going to spend a little time with it. So I'm just going to put a little, yeah, I need to do that. I'm just going to put a little tilde thing here. So we're not going to really revisit this. This is actually, most of these methods were back from the 1700s. This virtual power kind of came into popularity recently here in the 1900s through a guy named Kane, and they're called Kane's equations. And some of your software code are built on Kane's equations. Actually, one thing your book has pretty nicely is it tells you for the various dynamic solvers that you can buy, it tells you what methods they're built on. Are they built on Newton's methods? Are they built on Lagrange's methods? Are they built on Kane's equations or the like, which is kind of nice. So you can understand some of the idiosyncrasies. So Kane's equations is one way to do it. And it has some, some of the features that they claim are, they can deal with, in theory, they deal with holonomic and non-holonomic constraints. And I feel bad to throw that out there. We will get into these specifically, is the idea. Holonomic constraints are the ones that we're familiar with and are readily dealt with. They're integrable. The non-holonomic constraints are the difficult ones. Frankly, at this point, all of these methods people have adapted, and you can deal with holonomic and non-holonomic constraints in all cases. However, from a purist standpoint, people would say, well, virtual work, D'Alembert's principle applied to virtual work doesn't apply to non-holonomic systems. They'll say Lagrange does not apply to non-holonomic systems. However, they've been adapted in the way we'll use them, they do. Very quickly, non-holonomic systems, wheels, rolling wheels, vehicle dynamics, those invoke non-holonomic dynamics. So it is an important, not an ignorable issue. Okay, but again, this is just high-level overview, and I think I need to, I'm 3 minutes over, so I'm gonna about wrap it up. So I've got 2 more methods I'm gonna show you, and the big one, sort of the reason for signing up for this class, is method number 6. I guess I have it here, is Lagrange, or Lagrange's equations for rigid bodies. So Lagrange's equations. Lagrange's equations were developed by Lagrange, Joseph Lagrange. I have his 1788, but it's hard to say when these things go, exactly when this came around. I'm going to write, we wrote, I guess we've been writing the equations. So let's write it out. So Lagrange's equations are written like this, and you've seen them and used them, but I'm assuming, this, one of the big things of this class, I'm going to really introduce you in detail to Lagrange's equations. It's the counterpoint. This is the counter dynamic model. This is the counter way of developing equations of motion. You're familiar with Newton. This is the classic analytical energy-based way of solving, of writing these equations. And they're written in like this. The ddt of the, so that's just the time derivative, of the partial of t with respect to q, k, well, actually, let me, of the partial of L with respect to qk dot, and I'm going to explain what these are in just a minute, minus the partial of L with respect to qk equals a cap qk, with L is the Lagrangian, that's the name L, and it's equal to T minus V, and T is the kinetic energy, okay, so kinetic energy. So T is the kinetic energy. And so what would V be?
Potential.
The potential.
Dr. Canfield,
Yes.
I apologize for interrupting, but
No, thank you.
The video stopped updating right after 0.5.
Okay. Oh, hold on. That was my bad. That's why that showed up. Can you see us now?
Yes, sir.
Hey, excellent, Ben. I appreciate you doing that. Okay. Good.
You're almost at that hour mark.
Okay, good. Excellent. I'm going to finish this in the next 2 minutes, and then we'll stop this. Okay, so that's the potential energy. So just the energy of the system, Lagrangian energy system. The Q is the generalized coordinate. And, that's what this set particle kinematics, I think I introduced the idea of generalized coordinates here. So Q is the generalized coordinate. This class is going to get you hopefully get you comfortable to referring to Q. Think X, Y, Z, if you will, or theta 1, theta 2, whatever you're, for example. And then cap QK is the generalized force. So if we could just look at this a second and compare, so this is this guy's the big deal. The Newton-Euler equations of motion are the big deal, and this is the big deal. These are the two things that come out of this class, okay? And frankly, these apply to rigid and non-rigid systems. I mean, flexible and non-flexible systems, but we're gonna look at a flexible standpoint. So if we look at Newton's laws, we say the sum of the forces, we take all the forces acting on a body equal to mass times acceleration. In Lagrange, we say the total, derivatives of the total energy of the system equals these generalized forces, okay? So you can kind of see the similarities, but you also see the differences. One is a vector approach. I've got to take forces, they have to be written as vectors. In the other approach, I write them as energy. Is energy a vector? No, energy is a scalar. That's interesting, right? So I'm taking derivatives of a scalar. So I'll get a scalar. Now, yeah, that's interesting, right? Now, how is it, if I have a system, I toss this book in here, right? This book is moving in 3 space. So there's going to be, at least 6 coordinates, right? If I want to think in vectors, although rotation is not a vector, but let's just think 6 coordinates, right? So a vector, we take sum of forces of the moments, that'd be 6 equations, 6 vectors, right? How many energies associate with this book if I throw it in the air? 1. So that seems like a little discordant there, right? I've got 6 forces, but only 1 energy. How do we deal with it? Well, look at this. We're taking the partial with respect to QK. So here's the beauty of the energy method. I have 1 energy, but depending on how many coordinates I use to describe that motion, I have to take the derivative with respect to each of those coordinates. If I choose to write this book with 6 coordinates, I'll take the derivative 6 times, and I'll get 6 equations, just like I would get with Newton-Euler. However, if there's something associated with this book, maybe that, if I just spun the book like that, right? Now, obviously, it's not moving in 6 space, but I still have 6, I've got 6 forces and 6 moments and forces, right? But with Lagrange, I could say, well, I know that it's constrained to be on the table. So I'm down to just 3 coordinates. So I could just take derivatives with those 3. So, the energy method constraint, the beauty of the energy is anything that doesn't do work, doesn't contribute to energy, I can pull out of the equations. That's the beauty of the method. So it's powerful. It seems like there was a period of time, and there are some papers where people would say Lagrange is, the breakthrough of Lagrange is significant in that it can solve problems that Newton can't, or Lagrange can't deal with problems that Newton can. There's sort of this Lagrange-Newton war. I think they were probably ill-founded papers somewhat. So there's been a number, you can actually find papers that go to great lengths to prove that, that physics are physics, dynamics are dynamics, There's one answer. That's the beauty of engineering science, right? There is an answer. We're just seeking it. And if you got the right answer, Newton should point you to it, and Lagrange points you to it, okay? So at the end of the day, there's no difference. You could say, I just choose to solve all my dynamics with Newton, and I can solve the problems, and that is the case. You get the same exact answers. Keep that in mind. So why 2 methods? Why 2 methods? Well, we know, we could show an example, but we know depending on how we attack a problem, it can be easy or it can be really hard just because of the math we're stuck with. Our math is going to change. I feel confident that the way we do kinematics right now is going to change, hopefully, in the next 10 years because it's got a lot of problems. It's got some good stuff, but it's got some problems. But, depending on how, just the math is not, the way we write, X, Y, Z, that's a construct of us, right? That's not necessarily a construct of physics. So the different methods give you different ways of attacking problems. And so that's the benefit. Okay. So that's the idea. It's energy. It uses these generalized, so the features are these generalized coordinates. So the features are, I will say Q, the generalized coordinates. So they're generalized, right? I'm not stuck with vectors. I'm vector free. And I'm also, I eliminate, spell that right, eliminate all constraint forces. or the workless constraint. I should say the workless constraint forces. Okay, and then yeah, and okay, and then give me one last minute. Now there's sort of an overarching principle, Hamilton's principle, and I think what I'm up to next 7 is Hamilton's principle that I want to mention briefly. And Hamilton's principle would be an overarching method. Okay. We're not going to really treat it in this class, but just in my review, I want to cover it. Hamilton's principle is what I would call an overarching principle. It's a variational principle that minimizes energy as, okay, so Lagrange's methods are energy equations, and it gives you an energy balance. And they're derived from a minimization of energy. Newton's laws don't look like, they don't think about energy at all, right? It's just a balancing of forces. But we know to work, they have to, they have to minimize energy, right? Because that's how physics work. So it's in there. Hamilton's principle goes directly to the energy. So the idea is it's what we sometimes call a stationary principle or a minimization principle. And it minimizes the energy as it says the minimum of this function. So I'm going to call it the d alpha of this stationary integral. So I'm going to integrate over this integral, and I'll call it L t alpha dt equals 0. You could let this parameter be whatever you want. I made it L because it can be the Lagrangian. The Lagrangian is one suitable function you could put in there, but you could put in any function, the Lagrangian or another function. It just has to describe the system, the energy in the system. And, Hamilton's principle, the concept, just generally speaking, is this. If I have a particle that moves from one point to the other, somehow I want to describe how it moves. There is a true path, but I don't know that path. So what I do is I assume some path up here. And then I apply a variational approach, and I'm going to integrate over all possible paths. Okay, so I can write this path. I don't know this path, but this is some varied path, variational path. And I integrate this guy over these variational paths, and I find the actual motion is the one that minimizes this interval. That's conceptually the idea. To do this, you have to, know variational calculus, which could be a series of courses that you could choose to take. I feel bad. I chose not to take them. So I'm not a variational person. So I'm going to stop my discussion here. I'm stuck with Newton and Newton-Lagrange. Hamilton's principle is one way of deriving Lagrange. Frankly, I don't really see, I think when we talked about some of the problems around Newton, for example, I didn't really talk about problems around Lagrange. When I talked about some of those, like quantum mechanics and the like, you have to sometimes go back to the basics. And Hamilton's principle is a fundamental principle that in theory should start handling some of those other problems. Hence, that's where it shows up. For us, we are dynamics and machinery. We need to solve machinery problems at some day. So we're going to be a little more practical. Okay, so with this, I'm going to end this discussion, okay? There are a few other methods I'm going to leave this overview, big overview. So I've reviewed a couple vector-based approaches and a couple analytical-based approaches. Questions, discussion while you're stretching. Okay. So